Can you see the screen? Are the slides visible?
Yes, sir.
Okay. In this class, I'll be talking about the deadlocks. There is one small part left in the threads in multi-threading, that is to discuss about the assignments and some of the functions, POSIX functions, apart from creation, synchronization and exit. So that I will do in the next class. So this deadlock is something that appears to be more of theory rather than writing codes or uh, dealing with functions and system calls, but it is extremely essential in terms of I mean, when a deadlock happens in the system, nothing proceeds, so the system gets completely in a halt stage. So deadlocks need to be handled properly, otherwise there might be cases where uh, there can be serious computational loss in the system. Okay, so the topics will be what deadlock is, and in our real life also we face deadlocks, situation of deadlocks. So in the system, what are the ways to avoid or overcome deadlocks, handle deadlocks? We can go for prevention of deadlocks, avoidance of deadlocks, and detection and recovery. So there are three possible ways we can handle deadlocks: prevention, avoidance, and detection. And if it happens, we try to recover. So these real world scenarios are pretty easy to understand. So the first thing is, in the first step, in a traffic junction, we can see that there are cars coming from all the four sides, but there is a possibility of deadlock if all four of them approaches towards the junction. But if the lights are suitably operated, if one of them is green and the others are red or yellow, then there will be no deadlocks. But in this case, this is quite rare, and it can such a situation can trigger only if we find that all the lights are green. So cars from all sides will approach and nobody will be able to proceed. So these are the cases where deadlocks occur. The second example is a very narrow bridge where the cars or vehicles are approaching from both sides, and they are face to face, they are facing, and probably it is so narrow we cannot have space that they will pass on. Okay, so these are deadlock. And in the third case, there are, so in this case, in the first case, this traffic intersection is a resource, and these four vehicles are the it's something equivalent to the processes which are competing for getting the resource or acquiring the resource. In the second case also, this narrow bridge, the passage is considered to be the resource. In the third case, we consider two resources. One is the chalk and another is the duster. And here is a situation where one of the faculty, he's having the chalk. Probably there is only one chalk available, and he requires a duster to continue with the class. And the other faculty is having the duster. There is only one duster in the department, and he's not having the chalk, so he cannot continue start the class. But and the situation is a deadlock because none of them are willing to release the resource or voluntarily release the resource until he receives the other one and he completes the class. So they are quite desperate in not releasing the resource and holding it. So this is one case. They are not also willing to share it all, share the resource. Okay, and the resources are I mean, they are not willing to share. They want to use the resource, both the chalk and duster, in a mutually exclusive way, that the chalk can be used by only one faculty, and in both the case they are holding one resource and claiming some other, or requesting for, waiting for some other, and they are not willing to release it or voluntarily give it until unless their task is complete. And this rigidity probably creates a situation of deadlock. Okay, So this is the case, and uh, in case of computational system also, we often face such scenarios. So the resources, when you talk about resource, in a typical computing scenario, we can consider processors, the CPUs, the memory. Say you can think of a page frame, or it can be a shared memory which is shared by many other processes, and one process acquires it and the others they cannot share it, they cannot use it simultaneously until unless the process releases it, otherwise there will be a conflict. There may be other devices, input output devices, there can be communication links, uh, maybe files or a specific record of a file, semaphores, all these things. So in a computational scenario there can be many occasions where we have to deal with resources which are not in abundance, or the number of resource units of different types are much less in numbers than that the number of processes which requires it, and still uh, you have to ensure that the system is running without a complete halt. And also the situation is when the processes run, they may not be able to put or place their request well in advance. So a process before it starts running, it may not be able to figure out how many resource units it will require of a particular type. It depends on the input, it depends on the computational output and all this. So that makes situations that we illustrated in the last slide, if similar situation happens in a computational scenario, it becomes really difficult to handle such scenarios. So in 1971, it was long back when simultaneous or concurrent processes were allowed in the system in a time shared operating system. Kaufman identified four necessary conditions which leads to such deadlock situations, and these necessary conditions are easy to uh, guess also. One is the mutual exclusion. So if you are considering shared resource, then there may be problems, and if the shared resource need to be used in a mutually exclusive fashion that only one process can use and others they cannot use, then use of such kind of resources may lead to deadlocks. If the case is hold and wait, you are holding something and you are waiting also for something, in such a situation, as we found, deadlocks might occur. Non-preemption is another case. So it is not that if you are waiting for 1 hour, you say that okay, I don't want to take the class, let me release the duster and I leave. So nobody is going to preempt, or no process is going to be preempted until unless it receives the resource that it has requested and it completes its task. So that is another big problem. And finally, this is the circular wait. Okay, so in the previous example, say one faculty, he waits for some resource which has been acquired by some other, so he waits for the duster, and the duster is allocated to the other faculty, and the other faculty in turn waits for the chalk which has been allocated to uh, the previous faculty. So they are in turn kind of waiting for each other to release the resource and holding something. So it's a kind of circular waiting for each other. And in such a case, in case of deadlocks in the computational system, there can be multiple such processes and resource types involved. This may not be a simple two process or two resource type case. So one point that we can note here is that this box denotes a particular resource type, and dot represents the number of units of that type. So you can think that printer is a type of resource, and if there are three printers, we'll have three dots representing the three units. And if we have got CPUs, so this box may be the CPU. So CPU, if there are four CPUs, so there will be four dots representing four resource units of that particular type. Okay. So the point is the first three conditions here this denotes a possibility of deadlock, but if all the four conditions exist, then there is definitely a deadlock. Okay. So all the four conditions are required for the deadlock, and the first three conditions, there may be a possibility. Now, the existence of deadlock, to understand and to detect if there is a deadlock that has occurred, when in the system there are multiple number of resources, there may be say 4 or 5 resources which are competing for the resources, processes which are competing for the resources, and there may be 3-4 types of resources of different number of units. So to better visualize the situation, or specifically the circular weighting condition, uh, we often use resource allocation graphs. So we try to denote the dependency or the request and the allocation edges, allocation request in terms of some edges, and we denote the processes and also the resource types as nodes. Okay. And it becomes easy to visualize, as we found in the previous case also. So this is a kind of resource allocation graph. So the formal, we can describe it more formally, that a resource allocation graph G consists of V and E, where V is it consists of both the processes as well as the resource types, the boxes as well as the circles. And the edges consist of 2 types of edges are there. One is the allocation and the resource and the request edge. So as you can see, there is a requesting edge here, and there is allocation edge denoted by solid lines, and the request edge as dashed line. Okay, so there are 2 types of edges and there are 2 types of nodes, which through which this resource allocation graph is composed of. Now, this is an example. These are 3 examples of resource allocation graphs. Now, can you say that all of these denote a deadlock situation? If I start with this one first, is it a deadlock situation here? There are 4 resource types. Okay, R1, R3, R2, and R4. There are 4 types of resource, and as you can see, different types are having different number of units, and this there are 3 processes which are actually uh, requesting, and they are also holding some resources. So is this a deadlock situation? Just by visually looking into it, what do you think? Are you getting me? So is this a deadlock situation here? Hello? Is this a deadlock? The first one?
Yes, sir.
What about the second one and the third one? What about this one? Is this a deadlock here?
Yes, sir.
Is it a deadlock? See, there is a, can all of you hear me? So is this a deadlock? You see, there is a circular kind of there is a cycle that exists in this resource allocation graph. So we say that this is a resource allocation graph, this is another resource allocation graph, and this is another. So there are 3 resource allocation graph depicting 3 different cases, which might lead to deadlock, we don't know. So if I come to the second one, this one, you see there is a cycle here. So does this cycle mean that there is definitely a deadlock? Think and answer. Just try to see the request and allocation. Is there a deadlock? So what does it mean? This particular resource type R2, this particular unit has been allocated to P4. Is P4 waiting for some other resource? It is holding one unit, but is it waiting for some other resource?
No, sir.
No. So definitely, no matter what others are doing, P1, P3 and P2, P4 is not waiting for something. So P4 is already holding something. So definitely it will be completing and releasing this particular unit that it is holding, right? It might take 2 seconds, it might take 2 hours, but it will definitely release it. Now once it releases, then whose request can be satisfied after this? After P4 completes its execution and releases this resource. So who else can be satisfied?
P3, sir.
P3.
P3. You see, P3 is already having this unit of resource, but he has requested one unit from R2, which earlier it was held by P4. Now P4 has released it. So definitely this can be allocated to P4, P3. So now once P3 receives, now P3 is happy with both the resource units, one of type R1 and one of type R2. So P3 definitely it will eventually complete its execution at some point of time. Now once P3 has completed, it will definitely release the resources that it is acquiring. So which one it will release? It will release this unit, okay? And maybe meanwhile P2 also has completed and it will release this unit also, okay? So now P1 was holding this one unit of resource R2 and it was waiting for long for one unit of R1. It will definitely get either after P2 completes or P3 completes. So eventually we know that the sequence of completion will be P4, then P5, then P3 maybe, then maybe P1 or maybe P2, then P1. So is there a deadlock here?
Sir, won't P2 complete earlier than P3?
Definitely P1 will get the chance first. So then,
Sir, P2,
I mean, in
P2.
whatever way it is, I mean, this is one possible sequence. So the question is, will there be a deadlock
Sir,
here?
the P2 is not requesting for any resource.
No, it's not requesting. So eventually it will release its unit like P4. So if it is done early, so then P1 will get its resource and then P1 will be completed.
Okay.
So the point is, so the point here is when you draw the resource allocation graph based on whatever has been allocated to you and whatever you are trying to acquire, you have requested. So it's a request edge and the allocation edge. There may be a cycle of dependency, but this does not always mean that you have a deadlock. So when this cycle will definitely trigger a deadlock with certainty. So if each resource type has only one instance, then such a cycle with multiple processes definitely will ensure will make sure that there is a deadlock, right? But if there are multiple units corresponding to each type, like in this case, in the first and the second case here, this may or may not be a deadlock. Okay, then we have to analyze. I mean, there are algorithms which we can just figure out, write a small algorithm using this approach. Okay, the way we did. And this will be done later in this class. So this is how the deadlocks can be detected. So the first thing is, here there is no such provisions. You see, R4 nobody has requested, nobody is holding, so it is just an isolated resource type. But as you can see here, P3 will be requesting to R2, and nobody, and R2 it has been allocated to P1 and P2, and P1 P2 again they are requesting for something which has been held by others. So this is a typical situation. You see, these two cycles, they will never be they will be always be there, this dependency. So in the first case there is a deadlock. In the second case there is no deadlock, as we can see, although there is a cyclic dependency. And in this in the topmost case there is a cycle, as you can see here. This is a cycle like this involving multiple processes, and each resource type is having just one unit. So it can be guaranteed that there is a deadlock here. Okay. So if the graph resource allocation graph contains no cycles, then there is no deadlock. If there is a cycle, and if there is each resource type has got one instance, then also there is a deadlock. But if a resource type has got multiple instances, then the deadlock may exist. We have to analyze, and we have to answer it. Okay, so these answer. So the second one is having no deadlock, but the other two will be having deadlocks. So now handling strategies, it is we can take analogies that we are doing these days also. I mean, dealing with COVID situation. So COVID handling strategies, what are the strategies? Ensure that COVID never occurs using either prevention or avoidance policies, right? And the other one is a kind of reckless approach, allow COVID to happen, and then you detect it and through testing and recover it. Okay. So what are the possible strategy that we generally follow? Prevent means don't step outside your home till the vaccine comes. So if you really try for prevention, how long you have to wait? How long you have to wait?
Until the vaccine comes.
Nobody knows. It's a indefinite time. So you can think that it is something like indefinite postponement. Nobody knows when it is going to happen. The vaccine comes successfully and everybody gets vaccinated. So if you are really trying to prevent something, so you basically for 7-8 months, 10 months, you always stay indoors, and it's up to you how you manage. Now what avoidance means? Now this is something that many of us try to follow, but I don't know what it ends up with. So they go outside and make sure that definitely they wear masks, but they always stays at a safe distance. What that distance, how it is defined geometrically, we really don't know. So 10 meters or 5 meters from any other person, and everywhere you feel a crowd. So if you really want to satisfy that geometrically, you have to stand still, or maybe fly away from some place because others are approaching towards you. So this also is something very it will be tricky to avoid once you are outside. So if the prevention is followed, then no work will be done for you. I mean, you cannot do anything. Even if you target avoidance, you step outside, but probably you will end up doing nothing, because there are so many people around and you have to only work in the midnight. And the last option is allow COVID to happen. So you don't wear masks, you don't care about, I mean, you go to the crowd and all, and expecting that these days the infections, probably in many cases people say that it's not that much, you have grown up the immunity. So detection, so some symptoms, if it is found, you go for testing, and the recovery means you go to the isolation centers and then followed by several months of rest. So similar in case of, and probably most of us are doing this strategy. Okay, so prevention, avoidance, those days are gone, and we are sticking to this, and the outcome is unknown to us. In case of deadlocks also, uh, we can have similar analogy. So it can be prevention, avoidance, and detection and recovery. So prevention, what can be the prevention? How can we prevent deadlocks to happen? We target those 4 conditions. The Kaufman conditions. This is non-preemption. Then it is hold and wait. Then it is
Mutual exclusion.
just a minute, sorry. Okay, so in case of prevention, we actually target those 4 conditions, necessary conditions, that they should not occur by some means. And in case of avoidance, the strategy is we try to make sure that every time, so you make some calculations. So when you go outside, you say that, okay, I have to see that whether somebody is approaching towards me. If they are approaching, you are moving away. So every time you are calculating that if you are in a safe distance or not. So here also the same thing happens. Whenever a new request comes from the process, from the set of processes, a process requests for some resources of different types. After it has, I mean, it is holding something and it is requesting something. So some calculations need to be made to make sure that this request, if it is granted, it will not lead the system to a deadlock in future. So this calculation need to be done, and there is an algorithm called Banker's algorithm, which will come up with the checks. Okay, so if that state is safe, then you actually assign the request, or grant the request. So every time there is a new request comes, you make sure that that particular assignment, if it is done, it leads to a safe state. State means whatever allocations has been taken place, and then you actually make it happen. If it is not, you make the process stop. You just fix the process in the suspended state. That means right now the request cannot be satisfied. You just hold on. And when you are asking that you should hold on, you make sure that, till that point it is in a safe state. So you know that some of the processes will complete or release the resource, and after a certain while the request can be satisfied. So that was the strategy of avoidance. Okay, and this deadlock detection, as we found that there will be some kind of some means to detect the cycle, and not only the cycle, to see that whether the cycle truly indicates a deadlock situation. Okay, so we'll basically be talking about an algorithm here, a deadlock avoidance algorithm and a deadlock detection algorithm. So in case of deadlock prevention, which is the most simpler, or it is not very effective. So one thing is, the idea is to try to eliminate the conditions that might cause a deadlock. So the mutual exclusion is something that you cannot eliminate. So there are some kind of resources which need to be so these are shared resources, and they need to be used in a mutually exclusive fashion. You cannot share it, like a classroom cannot be shared by two faculties. Okay, so something like that. Hold and wait. This is something that you are holding something and you are waiting for something. Now how to eliminate that? The only possibility is, if you can guess your requirement prior to your prior to this process starting, only then you make sure that whatever I need, I just request all at once and I hold it and use it. So while holding something, I should not need to wait for something. So this hold and wait also is something very tricky, because for this you need to know your requirement well in advance. Then comes a non-preemption. So this non-preemption also, it is not always possible, because if a particular process is using a printer resource, now it has done half the printing, and now it is waiting for something, maybe some file to get unblocked, so that it can read the record and it can again continue with the printing. But the file has been it has been held by some other process which is holding for the printer to be free, something like that. So this non-preemption is difficult, because the process which has done half the printing, it cannot release the resource. It will be again mess up. So this is also not always possible. And this circular wait, uh, this probably can be easily avoided by framing some rules. What is that? In case of circular wait, to avoid circular wait, what we can do, there are different resource categories. Say for example, there are 5 or 6 resource categories in the system. So we try to order them, we try to put them in certain order. Like the CPU is the most valuable resource, then the memory, then comes a file, then comes a IO channels, and something like that. Okay, so the point is, the rule, when you request for a resource, the rule says that if you are holding a particular resource of level 2 or say level 3, and you are requesting for something, so you cannot request something that is below it. Okay, so you can always request something greater than that. So you have to follow that ordering. So if that happens, then also say for example, the duster is first comes a chalk, okay, and then comes a duster. So there is, if the ordering is something like this, so this is first and this is the second. So whoever comes, if he receives the chalk first and requests for the duster, The second person cannot acquire the duster and can and then request the chalk, because it says that if you are acquiring the duster, you cannot go below one level and request for something. Okay, so you enforce that this circular waiting situation never occurs. So you strictly uh, adhere to the numbering or leveling of the resource types. So this is one possible way. This is probably a feasible way to do this. But again, if you do this uh, unknowingly, or maybe trying to be too defensive, you often end up with slowing down the overall performance of the system. Because deadlocks, although these are very critical as an event, or I mean, when it happens, there is nothing to I mean, you just have to roll back the system. You have to lose some of your computation, but these are definitely rare. Okay, so deadlocks are rare. That's why this prevention and avoidance often is not actually used in the reality. But these are the ways where how you can try to prevent deadlocks, which may not be always effective, and it is really difficult to implement also sometimes. So next comes the deadlock avoidance. Here the key idea is decision is made as I mentioned. So every time, so you have got a particular state of the system. So the thing is, the state of the system is the current allocation of the resources to the processes. So we can maintain some kind of matrices, like if there are 3 processes, say for example. So for each process we have got one row, and if there are 5 resource types, so they can be represented in the columns. Okay, now we can say that okay, this particular process is having this resource type 2 units, this resource type 1 unit, and this is having probably this resource type 3 units, like that. So we can represent that uh, allocation state as well as the request, whatever it is done, in form of some matrices or vectors. So those the contents of those matrices and vectors together form the state of the system. Now if being in a particular state, if some other process requests for some resources, some computation need to be performed, and it need to find out whether the overall system's state will be safe after this request, or if this request has been satisfied. If it is satisfied, if it is safe, then it will be actually committed. Otherwise the process, the policy can be, the requesting process should be suspended for some time. And that means that the process will not be suspended forever, because the state which is currently the system is a safe state. So from the safe state, definitely some process will complete, and they will be they will be releasing resources, and the process which is suspended will get a chance. So the point is, I mean, if it is a safe state, so there is no question of deadlocks. But if it is an unsafe state, if you allow the grant if you allow the request to be granted, knowing that it will lead to an unsafe state, now this might be dangerous. So unsafe state does not also guarantee that it is a deadlock, but there may be some cases, or there may be some request patterns which will lead to these from this unsafe state to a deadlock state. So that's why the strategy says that every time we check if the allocation request leads to a safe state, that is granted. If it is not leading to a safe state, it is unsafe, the request or the particular process which requested will be made suspended. Okay, so all deadlocks are unsafe, but all unsafe states are not deadlock situations. So we'll take some examples and see what exactly it means. So avoid deadlock, ensuring that the system never steps in an unsafe state. So can you see this example? So here, so when we say the state of the system, so the contents of these matrices and vectors denote a particular system state. So now can we say, so what is this? This is a claim matrix. Claim matrix means there are 4 processes and there are 3 resources. So this is a claim. Claim means, what is a claim? How much of each resource each process could at most request. Okay, so this is a maximum request that a process can make. That means what? This process P1 can request at most 3 units of type R1, 2 units of resource type R2, and 2 units of resource type R3. Now, this does not mean that it will need to make the request all at once, but during its lifetime, it can make at most at a time, it can make the request of 3, 2, and 2. So that can be the at most maximum request that it can make corresponding to different resource types. And different processes, they have their different requirements. This is a maximum request that they can make. And this allocation matrix says that what is the current allocation of a particular resource type corresponding to a process. That means this 6 means, that means this resource type R1, 6 units of resource type R1 has been allocated currently to P2, or P2 is holding 6 units of R1 at this moment. Okay, so like that. And this 2 means P4 is holding 2 units of resource type R3 at this moment. So this is a particular point of time. So this is all at once. This is there. This is not going to change, but this allocation matrix will change with time, because if you get some new allocation, some request granted, this allocation matrix will change like that. And this is a resource vector. What is a resource vector? These are the number of units of each type that the system is having. So here R1 is having 9 units, R2 is having 3 units, and R2 and R3 is having 6 units. So this also is not going to change. So this vector R and this claim matrix C is not going to change with time. But this allocation matrix is so at a particular point of time, this is the current allocation state or allocation values. And what is this C minus A? What will be C minus A? If I subtract A from C, what is this?
Number of units remaining in resource.
Yes, so you have already said that P1 can or P1 declared that I will be not requesting more than 3 to 2 at most. Now it says that P1 has already been already requested and it has been allocated 1 unit. So at most what it can make the request? 2 to 2. So this can be the maximum claim that it can make right at this moment. Okay, so that is the current state, and this is the available vector. So this also is going to change over time. So all this C is going to change over time. Okay, what is available vector? So available vector means the number of units of a particular type that is currently available for allocation. So you can see that only resource type 2 and 3 are available. Resource R1 is none of the units are available at this moment, and these may be the possible claims in future. Okay, at most. So now the question is this a safe state? How can we say that if this particular state of allocation is a safe state or not? Now when we say it's a safe state, yes.
More than 1 unit is available.
More than 1 unit? Where?
Sir, resource, more than 1 unit of resource is available.
Where? Which resource type?
Sir, available vector.
That is available, fine, but my question is what do you mean by safety here? What do you mean by safety?
Sir, deadlock is not possible.
So how you know this? See, this is the current allocation. Now this is the current claim, or this may be the future claim. So how you estimate? So what can be the worst case request that can come in the system? What can be the worst case request? That at some point of time P1 request all its claim, I mean remaining claim, pending claim. P2 request all its pending claim. So they just do it all at once. P1 says that I want 222, P2 says that I want 001, like this. Now if such a request comes, that is the worst case requesting scenario for all the processes. Now, can the system handle that requesting pattern? Or even if those extreme pending claims occur, will the system be able to get rid of the situation? Will there be some exit path, like somebody will finish and somebody else will finish, like that? That is a question. Can we calculate that? Can we find it out? Have you got my question? So the safety will be judged based on the uh, based on this C minus A. So if the C minus A, whatever it is pending, is requested all at once from all the other processes, will the system be able to uh, resolve the requests in some form, so that eventually P1, P2, P3, P4, in some order, they will be completing their tasks after getting the allocations. So what we see here is, you see, uh, what can be, so these are kind of hypothetical requests that we are considering. So whose request can be satisfied right from the right at this moment, if this is the available vector out of P1, P2, P3, P4, whose request can be satisfied at this moment based on the availability? So you
P2,
match
sir.
which one? P2. So you have
P2,
to
sir.
match one by one the rows of this C minus A with respect to the avail vector V. So if you find that if you find a row which is having lower demands or lower than equal to the demands or corresponding to the availability, you now can safely say that that process, so no matter, so even if all of them, all of the four requests say right at this moment, so definitely I know that this P2's request can be satisfied, that can be guaranteed, right? So P2's resources, if it has been granted, say P2 requests, and the system will definitely grant. Now once it is granted, P2 will eventually finish, complete its task. So what the P2 will do then? So this P2's claim, pending claim, is less than equal to the avail vector. If that is so, then P2 will be granted. Say for example, I mean hypothetically you can say that P2 will be granted. So if P2 is granted, then what P2 will do? It will complete its task and it will release. What it will release? It will release all that has been allocated to it, right? Are you getting the point?
Yes,
So
sir.
if P2, so we assume that okay, all are requesting. So can I satisfy any of the processes request? Yes, I can. That is P2. So if I satisfy, then P2 what it will do? It will definitely, it will not only, it has not only claimed this, but it will also it will release all of this. I mean, what has been allocated to it. So what you will now you can do, you can think of that this row will be added to this V, right? The second row of allocate matrix will be added to the avail vector. So now avail vector, you see, after this allocation, after the assuming that P2 has been completed, so avail vector is the resource units has increased, and you see that this whole row here, it's of no use. Now the P2 is out of content like competition. So now with this modified avail vector, who else can be satisfied among P1, P2, P1, P3, P4? Who else can be satisfied?
Sir, all of them.
Anyone?
All of them, any of them. So let us assume that now we choose P1 to be that, right? So if we choose P1, you see P1 also uh, actually, so once P1's are says P1's request is satisfied, because this row is less than this, so this will be eventually be added to this pool, right? Whatever P2 P1 is holding. So now this has increased further, so it's from 6 to 3, it has been reached 7 to 3. And so these are all hypothetical situations, so you are trying to calculate it in the back of mind, that what is going to happen uh, if everybody requests all that they need at once. So now P1 P2 got out of competition, so now who else? Now definitely we can go for P3 next. So P3 comes, so P3 also releases, you see, once P3 is chosen, P3 releases this, so this becomes even more. Now once these three are done, P1, P2, P3, how many are left? Only P4 is left. Now one process cannot lead to a deadlock situation, right? So definitely it's up to that process. So what this means that this is definitely going to be a safe, this state is safe, because no matter whatever way they request, even if the maximum pending request they make, then also there is a always a possibility that all of them will exit. And what can be the possible sequences? The possible sequences can be P2, P1, P3, P4. It can be P2, P3, P4, P1, because once P2 gets completed, all the three are, they are, I mean, their request can be granted. So there can be several possible sequences for towards completion, right? So this is how we actually determine whether a system state is safe or not. Okay, and what is a how we interpret a safe state? Determine the contents of allocation matrix, available vector, the claim matrix, and all this. So now, uh, is this state safe? Now this is a state. I mean, this is a system state, initial state. And now in this situation, P2 requests this set of resources. So the question is, can we grant this request? P2's request 101.
Yes, sir.
You see, if I say we are not actually truly committing, but if I assume, say theoretically, let us assume that P2 has been requested, P2 has been granted this request, then what is going to happen? How they are going to change? Claim matrix is not, this is fixed, this is not changed. Resource vector, so these two never changes, so only the change can take place after a process completes or after a request is satisfied, is the allocation matrix C minus A and the avail vector, right? So now if I assume that P2 has been granted this, assuming, then what happens? So the avail vector, it will be 1 1 less, so 1 gone from this, 1 gone from this, and this becomes 0 0 0 1 1, right? And this value is actually getting added to this P2's pool, right? And from 511 it becomes 612. So if you can look into this previous case, you see this is the same case. So after getting this granted, hypothetically, we end up with a state which, because we have just now made the calculations, so we know that this is a safe state, right? So this is a safe state. This allocation, if granted, leads to a safe state because we have just now calculated it. So therefore, the request will be granted, can be granted. But if I make this request, instead of P2, P1 makes a request from that initial state that I want 101. What is going to happen? And if I force this allocation to P1, so P1's figures will change. So this will be added to this one, and this will be the new changed values, right? 201. Now the resulting state, and definitely this from the avail vector, so this value will be subtracted from the avail vector and it will be added to the corresponding P1 row in the allocation matrix. So will it be a safe state? This resulting state, will it be safe? It's very easy to check. Will it be safe?
No, sir.
No, sir.
This is very simple to see. You see, all these processes in the R1, they require how many? The pending request is they need at least one to complete, right? P1, P2, P3 requires at least one resource unit to complete, and P4 in fact requires 4. But in the availability, in the avail vector, how many units are left with R1 at this moment? 0. So if I commit this request to P1, will this state be safe? Can you find out a safe sequence of completion? It's not possible, right? So this state is not safe. Okay, so this allocation if granted leads to unsafe state. and this request cannot be granted. So what will be the fate of P1? So P1 will be temporarily suspended. Now the point is, so this request cannot, we say that this request cannot be satisfied right this at this moment, does not mean that this cannot be satisfied forever. It might happen that after say 5 minutes of time, this P2 decides to release maybe all of the resources, or maybe two of the resources here. Maybe P4 decides to release two of the resources from R1. Nobody knows. So if that happens, P1 will wait, and then definitely at some point of time it will be able to satisfy. So the thing is, this unsafe state means that if you commit this, it might lead to a deadlock, uh, and this is very obvious that if P1, P2, P3, P4 all simultaneously makes a request that their pending claim, it will lead to deadlock. So that's why this is deferred and this P2 is suspended for the time being. So the algorithm is very simple now. So the logic is also very simple. So this is known as Banker's algorithm, and this has been proposed by Dijkstra in 1977. I mean, yes, around 70s, 80s it was proposed. So this is what a state system state means. It is defined as a resource vector, avail vector, claim matrix, and alloc matrix. There are n number of processes, n number of resource types. And what the resource allocation is, so first it checks whether if the if so what is the request is this: if the alloc this uh, I, so the for the ith process, so I think I have to write this. So this I for the ith process, so this pi, for the pi it has made a request, this one. So this star means that particular requesting. So star means request of type R1 corresponding to type R2, type R3, like this. So this request asterisk means the entire row here, this one, I mean this one. Okay, so if this whatever it has requested plus whatever has been allocated to it, if this exceeds its claim, what does it mean? This ith process, it has been allocated already, the allocation where you can find this A of matrix A I star, plus now you are requesting this much, and if I add these two, it exceeds the claim. Does it make a is it a valid claim? Is it a valid request
No, sir.
made by P1? Because your claim says that this is your, so you cannot, you can never exceed your claim, because this claim says that you probably beforehand you know what can be the maximum claim at some point of time, but now you are violating that. So if that happens, it's an error message. Okay, if that is not the case, then the request whatever you have made, if it is greater than available, that means whatever you are requesting is more than what is available here. So it's like one by one the elements of the vector are compared. Sorry, I mean, if you are requesting more than what is available, then you have to suspend, because there is no way of process. So you have to just wait for this. But if it is not the case, in fact in our case it was not that case. So it's 101. So it was 101 and it was 112, you see. So this is less than this. So in our case, in that example, we actually got into this else case. Now if this is the case, then we define a new state by doing this. So define means assuming that the request has been granted, so it is assumed. So now this is how we form the this new state. What is this? In the alloc, you assume that your request has been allocated, so that's why you are adding the request to the particular ith row of that alloc matrix A. So you get a new allocation. How the availability get changes? Availability will be subtracted. So because you have been allocated, so available minus request. So that is how you get a new state, and which you check for safety. So you basically, this new state that you have that you obtain, define a new state. So new state dot alloc and all this you can write, So these are the different fields of that say structure variable, state structure. So the safe is another function that you call, which will check the safety of this new state. So if it is yes, then you carry the allocations. If it is not, you restore the original state and you suspend the process. That is what it says. So this is pretty simple to understand. So the next step is how we check the safety of this. So again, I just mentioned it for completeness. So here the safe, it will accept the state that has been formed in the previous algorithm, and it will return either true or false based on the safety. So the safety is again the same, the current available. So the process, the rest of the processes means what it does, it will, the rest is a set of, so rest is a set which is initialized with all the processes here. Okay, and current available is a temporary available, so the avail vector should not change. So that's why this avail vector is actually copied to this current avail, the current availability, so which will change in different iterations while it checks for the safety. Okay, and then we use a boolean variable possible which is set to true. So it's a while condition. So what it does, find the process pk in the rest such that, so that what we just now did in that example, such that its claim minus the its claim, that was original claim minus alloc, is less than equal to current avail. So this is c minus a. So this is what c minus a is. So if the c minus a is less than the current availability, that means that can be satisfied. So if it is the case, then we actually don't do anything. You simulate the execution of pk as if pk completes. Now once it is complete, then what we do, if we find such a case, this condition is true, then current available is incremented with the allocation of k. That means that particular process will release whatever it has been allocated to it, because this it will receive the current available and it will eventually release. So the thing is, this alloc gets added to the current available that we just now found. So in that way, current available increases, the contents increases, and from the rest set you remove pk, and you keep on doing this. So in the next step, again you go back and you check this, if there are some other processes which are found. If no more processes are found, that is in the last example, that means what? So if it is not possible, then it is false. If it is false, it comes here. And exiting from this while loop, if it finds that the rest set is having some resources which you have not been able to satisfy, then definitely it's a deadlock. Definitely it's a unsafe state. So the illustration that we found. But in the previous case, we found that first P2, then P1, then P3, P4. So one by one, the PKs will be selected, and they will be depositing their allocated resources to current avail, and they will be removed from the rest set. Okay, so this is just the first algorithm, the first procedure which calls safe, and this is how the safe executes and it returns either true or false. So is that fine? So that is what we discussed. So what are the drawbacks of the banker's algorithm? The first thing is the maximum resource requirement must be stated in advance. Okay, so to have this algorithm implemented, you have to know your claim. The claim matrix need to be known, and that is hypothetical, as we found. I mean, this is not always possible. And the processes under consideration must be independent. No synchronization requirements are allowed, and there must be fixed number of resources to allocate. Okay, so if the resources keep changing with time, that means what? The I mean, this vector, this resource vector r, if this r keeps changing, then also it will be difficult to fix it, because you calculated with some r and then r got reduced, and then the safe state became unsafe later on. So this is also not possible, and no process may exit while holding the resources. And if a process exits while holding, then it will be undecided, so its resource will not be added to the available pool. So the major drawback is here. So the resource requirement must be known in advance, and that is not possible. Okay. So this is one, and I think the other algorithm is the deadlock detection algorithm. And because it is just 1 hour past, I think this will not take too much time, but I can take it in the next class. So there are only 2 slides or 3 slides. Okay, and this is also a very simple algorithm. So let me discuss this algorithm in the next class. So if there are any questions, you can ask me. It is pretty simple. It is deadlock handling.